Hi guys, I have good news and I have bad news for you. The good news is that Topographic Map Lab is the last lab you have to do this semester. The bad news is it's another one of those challenging labs. So I'm going to film this and hopefully this will help you in completing your lab. So first of all, a topographic map is a two-dimensional map, right? It's a piece of paper that represents the three-dimensional surface of the Earth. And that's in fact what topography is. It's basically where are the hills and the valleys and the canyons and the mountains and things like that. And the way that the topographic map shows this third dimension of elevation is in these things called contour lines. Contour lines they're usually going to be brown on a topographic map, and they are lines of equal elevation. And I should say when we talk about topographic maps, or topo maps as geologists refer to them, it's going to be called a quadrangle, and a quadrangle is simply the map sheet that you have. And on these maps, in addition to those lines of equal elevation, those contour lines, there's all kinds of other symbols that will show you where there's forests and orchards and swamps and coral reefs and shipwrecks and pipelines and all kinds of stuff. And so I actually have a link right here that will take you to the United States Geological Survey, a page that shows you all of the official topographic map symbols that are used. Now, when we're working with these topographic maps, in addition to all those symbols, there's other things included, like magnetic declination and a scale. You're going to see a ratio scale. Many of these maps are 1 to 24,000. What that means is 1 inch on the map is 24,000 inches in real life, or 1 foot on the map is 24,000 feet in real life. So, when we look at these topo maps, like I was saying, the biggest thing that you are going to notice are the contour lines. And there are rules that govern how the contour lines are drawn. So every point on a contour line is the same elevation. So for example, right here we see 100, 120, 140. Well, every place on that 100 line is 100 feet above sea level. Every place on the 120 line is 120 feet above sea level. Everything in between those two lines is some elevation in between 100 and 120. Now, the contour lines can never cross because you can't have a point on Earth's surface that's multiple elevations. Every place on the surface has one single elevation, so the contour lines never cross. Another special contour line you will notice looks like this. It has these little lines pointing inwards. We call them hatchers. This is a depression contour. It shows that right here there's like a little sinkhole or a little crater of some kind. And that depression contour will always take the elevation of the lower contour line. So what we see is we're at 100 there, 120, 140, 160, so we're going uphill in this direction. But right there, what this is telling me is if I was walking along here, I'd hit 120 feet above sea level there, I'd hike a little bit higher, and then I'd drop down lower in that little depression there. The last thing that's really noticeable about these contour lines is they form V's. Do you see what I mean by a V right there? And what this dashed line represents is a stream. And these contour lines form these V's where they cross streams. And the tip of the V, or the point of the V, always points upstream, right? See, 120, 140, it's higher elevation here, lower, that's upstream. So once you get the hang of reading these contour maps, you can start being able to really tell what the topography of the area would look like even without visiting the area. Things like if all of the contour lines are very close together, that means you have a very steep hill. If they're very far apart, it means you have a flat area. If you see those hatcher marks, it means you have a little crater there. So in any case, you're going to practice in the lab reading some of these contour maps, these topographic maps. All right, on maps, an important skill to have is locating where you are on Earth's surface. There's a number of different ways you can do this. One of the classic ways is latitude and longitude. Right? We have these lines of latitude measured north and south of the equator, and the lines of longitude measured east and west of the prime meridian. Now, latitude and longitude measurements are in degrees, minutes, and seconds. And this is kind of a weird system because it's a base 60 number system. For instance, 1 degree equals 60 minutes, and 1 minute equals 60 seconds. And this all goes back to the Sumerians and their weird base 60 number system. I don't use latitude and longitude that much. I tend to use a more modern way called the Universal Transverse Mercator System, which we'll go over in a moment. Now, another way of locating land is the Public Land Survey System. And I go over this because if you buy property in many of the states of the United States, your deed will actually list your property location using this system. It was devised in 1785 to survey the new territories that the United States was acquiring. And basically, they set up this public land survey system as a grid system to measure these different locations. And so let me show you how this ends up working. So the United States would acquire a new property and or new territory, right? They bought the Northwest Territory and the Louisiana Purchase and all of those things. And they'd have surveyors go in there and they would survey a baseline and a principal meridian. And then from the baseline, they would measure townships north. See where it says T1N? That means this row is the township, the first one north of the baseline. There's T2N, that's the second one north. And then you'll have the T1S, the first one south, second one south, and so on. And then we have these ranges. See how this says R1E? That means this is the first range east, the second range east, and so on, east and west. So we have this basic grid system. Now these townships and ranges, that's 6 miles by 6 miles. That's a huge amount of property. So this was subdivided into sections. And you'll see the sections always start at number 1 in the northeast corner, and they go 1, 2, 3, 4, 5, 6, and then we drop down 7, 8, 9, 10, 11, 12, back and forth. Now, even if you have like a lake over here or the ocean or something, you do not number these 1, 2, 3, 4, 5, 6. 10 is always below 3. 14 is always below 11. Now, these themselves are 1 mile by 1 mile square. And that's still a lot of property. Back in 1865, the United States passed the Homestead Act. And according to this, you could travel west and you could stake a quarter section of land as your own property. And a quarter section is exactly what it sounds like. It is a quarter of one of these sections. So, for instance, you might stake out this quarter right here. And that is the northwest quarter. And how do I know that? On these maps, north is always the top of the map, west is always the left, south is always the bottom, east is always the right. So your deed, if you staked out this piece of land, would say that you're in the northwest quarter, section 11, township 1 south, range 2 west, right? Because this is our quarter. It came out of section 11. Section 11 fit in there, which was T1S, R2W. Now let's say you had 4 kids and you wanted to equally give them land. You might subdivide your quarter section. You might give one of the kids this part. Well, that's the southeast quarter. So that kid's deed would say that they own the southeast quarter of the northwest quarter, section 11, T1S, R2W. So it always goes from the smallest piece of property to the largest piece of property. And like I said, I go over this because, well, Texas doesn't survey like this. Many of the other states do, and you might someday own property and want to know what that deed is actually saying. All right. So I mentioned earlier that I tend not to use latitude and longitude. I prefer to use the Universal Transverse Mercator System, also known as UTM coordinates. And this again breaks up Earth into a grid system. And you can see the grid system right here. And basically what you end up measuring is you end up having an easting measurement and a northing measurement. So there is, for each one of these grid sections, an origin point. And you are going to measure how many meters east of your origin you are and how many meters north of the origin you are. And the numbers are listed in shorthand on the map. So for instance, if you're 450,000 meters east of the origin point, the map actually shows it like this, 450 and then the 3 little zeros. So if you ever see those things, that's your UTM coordinates. All right, in the lab, you are going to have to take a bearing. A bearing is what direction you are heading in. Like if you're going for a walk or something, or if you're watching like old movies like Top Gun, and you have Maverick in there saying, "I'm bearing 090, following the Russian MiG." What he's saying is he's flying east, following a Russian airplane. And 090, right, if we use azimuths, 090 is east. If he had said he's flying 330, that would mean he was flying kind of northwestish. So you will have to measure one of these bearings, or at least estimate the bearing. And just remember, it's using those azimuths that we went over way back in plate tectonics lab. All right, another thing you'll have to do in this lab is you're going to have to draw a topographic profile. That's basically where we slice the Earth in like a cake, and we look at it on its side so we can basically see where are we going uphill and where are we going downhill and all that kind of good stuff. And this might seem like it's going to be quite difficult, but actually it's not, and it's kind of fun. So you're going to be given a topographic map very similar to this one. So here are my contour lines, right? That's 700 feet above sea level. Here's 600. These are streams, right, in blue. And we are going to slice right along here from A to A prime, okay? So how we're going to figure out where we're going uphill and downhill and stuff, we're going to take a piece of scrap paper, set it from A to A prime, and every place we hit one of these contour lines, we're going to make a little mark, and we're going to write down what that elevation is. Then we are going to take that scrap paper to a grid. Notice my elevations are right there, and there's where I mark down where I hit those different contour lines. And so what I do is I say, okay, right there I hit 300. Right here I hit 200. See how I put those little dots in place? Now be very careful. One of the biggest mistakes people make when they're doing this, they're like, I hit 300 here, and they put the dot way over here. And it's like, no, that's not where you hit 300. It has to be right at the spot where you hit 300. So you put all of your dots in there, and then you play connect the dots for adults. So we're at 300 here and 200 there. That tells me we're going down. And then 200 repeats, which means, well, I was headed down, down, down. I have to reverse and come back up. There is a little bit of artistic license. For instance, you could have drawn this being deeper like that. That's fine. You just can't hit 100 because you never touched that elevation. So there's a little bit of, you know, little art involved in drawing these profiles. So on your lab, you're going to be given this public land survey grid. So notice we have R3E, R4E, T2S, T3S. You're going to have to figure out where different parcels of land are located. You're also going to have to figure out how many acres the people who own that property have. So just remember, one of these sections, one full section there, is equal to 640 acres. Okay, so you're also going to be given this map here. We have to figure out the contour interval. That means for every one of these contour lines, we are changing elevation how many feet. Well, this dark line is 800 feet. This dark line is 900 feet. So we're going 900 feet in elevation change. And we cross 1, 2, 3, 4, 5 lines to do that. So that means 100 divided by 5 is 20. Each one of these represents a 20-foot elevation change. You're also going to have to figure out what the elevation of some of these spots are. So for instance, spot 1, we have 800 here, and we're going downhill, so 800, this would then be 780, this would be 760. See how 1 is close to 760 but not quite sitting on the line? Well, that means it's some number close to 760 but not quite there. So you might write something like 758. Okay, so that's how you're going to estimate those elevations. And then you are going to draw your profile from A to B. So you take your scrap paper, right? We have A is right on the edge there, B is right here, and I'm going to mark every place where I hit one of these contour lines, right? So this one is 900, this is going to be 880, this is going to be 880, and this is going to be 880, and this is 920, 940, right? Because I'm going uphill here, and there's one of our depression contours, so I know it takes the elevation of the lower contour line. So then I'm going to bring that down to my grid here, and I'm going to set it right there, and right there is where I hit, what was it, 960, and then I hit 940 right here, 920 right there, and 900, 880, 880, 880. So I would end up then happily connecting my dots. Notice I repeat 880 a few times. Well, that tells me here I was going down. I have to curve back up. Oh, I was going up, but now I have to curve back down. And you guys can complete the rest of that profile. But basically just be very careful where you place your elevation points. You will complete another profile on your own. Here's the map you're going to use from A to B. And then A will be on one side and B on the other. And you get to show me the profile there. Then we have this, where you get to draw a topographic map. Well, you're given a whole bunch of numbers on here, and you are supposed to draw a map using a 10-foot contour interval. So we're going to find a number that is divisible by 10. How about 90? Well, I'm going to draw my 90 line right here like this. Now, why did I pick it that way? Well, every point on this line is equal to 90, so I have to be equal to 90 there. And everything on one side of the line is going to be less than that elevation. Everything on the other side is going to be greater. And then because this is a stream, remember, they kind of form that V shape where you cross streams. I know I have an 80 elevation right there because 78, 84, 80 is between those. I have 100 right here. I have 110 right here. And notice these lines can curve. Because I had a curve around 107, right? 107 is less than 110, so I had to kind of curve that line. And then I know I have a 120 here because I have 122, 125, and so on. So with every one of those lines, on one side of the line, everything should be less than that elevation, and on the other, it should be greater. So you get to do that on this one. Just make sure you notice that you're using 20-foot contours there. And remember, these little dashed lines, those are streams. Now, the last part of this map is using an actual topographic map that is loaded into D2L. So you can download an actual map. And you're going to have to find things. You're going to have to find like the latitude of the northern boundary or the name of the map and stuff like that. Well, I'm going to give you a little clue of how to find these things. This is one of my own topographic maps. And for example, this is kind of the bottom right-hand side of the topographic map. There's the name of the map. There's the year it was published. This right here, this 103.5230, that is the longitude of the eastern side. This 3645, that's the latitude of the southern boundary. Other things you can see on here. I'm going to move this here in the center. Here's our scale. Notice this is a 1 to 24,000 scale map. We also have a scale showing how long a mile is, as well as kilometers on there. And it tells us our contour interval. It's 20 feet right there. If we look here, we can see in red, that's one of those public land survey sections. So this is section 10 in that map. We can also see the magnetic declination right here. So GN, that's our geographic north, MN is magnetic north, and the important thing is to see that it's 12 degrees at this location. Now the last thing I wanted to show you on this map, I'm going to kind of move it down this way. These brown lines are all those contour lines that I'm talking about. And you see out here they're farther apart. Well, that's because that's a flat area. Right here, they're closer together. So if you went for a walk from here up to here, you'd be walking across a flat area, and then you'd have a steeper hill right in that area. Now, as always, with these topographic maps or with any labs or any of the activities that you're doing in the class, if you have questions, always contact me and I will do what I can to help you.